Hello everyone, thank you very much for having me here. Today I'm going to present a new method of broadening a metasurface bandwidth using first-order approximation of surface impedances. This work was done in University of New South Wales, Canberra, under supervision of Dr. David Paul in collaboration with Andreas Holk from IEE Luxembourg and Dr. Michael Liu from the Nonlinear Physics Department at Australian National University. So why broadband metasurfaces? First, we see that more and more studies of metasurface now focus on finding potential applications, and one of several important issues that need to be addressed in promoting metasurface for wider application is the problem of narrow bandwidth. So for example, here we have a low-profile communication device in the terahertz region, or we want to have low-profile collimating devices in microwave region. One solution that we can use is by using wavefront manipulation offered by metasurfaces. In some applications, the metasurface needs to work independent of frequency. For example, in a lens, it needs to maintain the same focal length of a broad bandwidth. And in conventional optics, this can be realized by combining two individual lenses called achromatic doublets. In the metasurface, we can actually realize the broadband achromatic operations by controlling higher order phase terms, such as group delay or group delay dispersions. Therefore, it can actually be realized without sacrificing the low profile structure of the metasurface. To achieve large variation of phase delay or group delay for broadband achromatic operations, several platforms have been used in metasurface designs. For example, here, pillars of dielectrics have been used in optical metasurface. However, the lower frequencies, such as microwave and millimeter wave, this could be problematic since the required structures would be heavy and difficult to integrate with electronic components. Another platform for achromatic metasurface is geometrical phase or Pancharath-Berry phase. This implementation requires cross-polarized transmission, which inherently limits the efficiency. The third platform is using filter synthesis theory to realize the metasurface. However, the resulting devices have numerous layers, each with different thickness. Therefore, the device fabrication is complicated and not easy. To achieve high-efficiency transmission operation without changing the incident polarization, we can use Huygens metasurfaces. Using this approach, full control over the transmitted beam can be realized by conditioning the meta-atom to exhibit strong magnetic response in addition to electric responses. For wavefront manipulation, the concept here is to excite properly phase-shifted electric and magnetic dipoles in equal amplitudes, such that high transmission copolarized operation can be obtained while tuning the phase over 2π. In the realization, three metallic patterns layers can be used, where each layer is modeled as electric sound admittance or impedance. Here, metasurface has been realized in the optical region, where each meta-atom is modeled as a position-dependent admittance. In the later works, it was shown that shunt admittance or impedance can be solved in a closed-form analytical expression. Therefore, using this surface impedance approach, we can obtain robust and a relatively easy conversion between macro requirements of the metasurface into realistic meta-atom implementations. However, reported works using this surface impedance approach are mainly for one frequency operation, resulting in narrowband transmission performance. We know that surface impedance approaches are not exclusive to metasurface, where they have been used earlier in waveform manipulation using reflect arrays and high impedance surfaces. For example, this work by Luukkonen in 2008, which focused on two types of most commonly used structure in reflect arrays, which is metallic patch and metallic grids. In another work by Steven Piper, we find that sub-wavelength scatterers have been used as an element for beam steering reflect arrays. Each individual element here can be tuned to work in a phase requirements for a specific waveform control. And what interesting here is that patch structure of various geometry has been evaluated in terms of their bandwidth performance. We see here that by tuning the geometry of crosses into square patch structure, the bandwidth can be improved almost 3 times. We find that this method of bandwidth enhancements is relevant for metasurface considered in our design, which is based on surface impedances. More importantly, it does not involve polarization conversion or using multi-layers approach. In a series of studies, we try to follow this approach of bandwidth enhancements using surface impedance model of the Meta-atom geometries. We start from simple fundamental question, which is what is the bandwidth limit of copolarized single resonance metasurface. We then propose a synthesis method based on first-order approximations of the surface impedances and use it for realizing broadband achromatic Huygens metasurface. The overall goal here is to obtain metasurface with copolarized, high efficiency, and broadband operation. And here is a simple requirements of broadband metasurface compared to a narrowband metasurface. We see that to realize broadband operation, each meta-atom needs to have a phase profile with slow variation to frequency. What happened in narrowband metasurfaces is that they try to match this phase profile in a single frequency operation, which can essentially realize waveform control, but only in a small bandwidth. Therefore, to realize broadband operation, each meta-atom should match the slow variation of phase requirements over frequency. In terms of single resonance model, we can already see that a broadband metasurface can be obtained by meta-atom that has low Q factors. The question now is how to realize these controllable Q factors in each meta-atom resonance. What we propose to obtain this Q factor controllability and therefore broadband metasurface is by using first-order approximation to the surface impedance. Here we see that a meta-atom which are represented as surface impedance can be fed into a simple LC resonance circuit, either in series or parallel configuration. The L and C requirements can be analytically obtained by using this formula, where here X is the imaginary part of the impedance and X prime is the derivative of the frequency, and omega 0 here is the center frequency. These derived LC requirements can facilitate the design of realistic structure. Here the meta-atom is realized as a simple dog bone structure, and LC for LC series and for LC parallel, the meta-atom is realized as a inverse dog bone structure. And then we implement this method into a broadband anomalous reflection problem in millimeter wave regime. We fabricate metasurface samples for operation within the W band and measure the far field performance using bistatic antenna setup. A narrowband metasurface was also fabricated for reference using single frequency feeding approach. We see that here the bandwidth of the broadband metasurface is 15 GHz, equals to around 18% fractional bandwidth. Compared to the narrowband metasurface, significant improvement can be obtained where in the narrowband metasurface, only fractional bandwidth of 9% has been achieved. Next, we use the same method to implement broadband operation in transmissive Huygens metasurface case, where in the Huygens metasurface, 3 layers implementation is used. Each layer can be modeled as surface impedance. Therefore, first-order approximation can be used to obtain bandwidth enhancements in this surface impedance approach. We designed the metasurface to work in the microwave regime with a center frequency of 8.8 GHz, and here is the illustration of the Meta-atom with outer layers and inner layers. More detail on this work can be found here in this paper, which has just recently been published. And by using the proposed method, dispersion engineering of the Huygens metasurface lens can also be realized. This flowchart here, this flowchart diagrams illustrates how we implement the dispersion control using Huygens metasurfaces. First, we design the group delay requirements for each metasurface as shown in these 3 curves. Here, n equal 1 is a metalens with increasing focal length over frequency, and n equals 0 is an achromatic metasurface. From these group delays, we obtain the phase profile of each meta-atom, and then using equivalent circuit impedance, we obtain impedance profile in each layer. Then, by using first-order approximation, we analytically obtain the L and C requirements for each meta-atom, as shown here in this figure. We also evaluate the performance of the metasurface using scattered fields from point-dipole model, where we see that the metasurface can have a focal length similar to the dispersion engineering being implemented. To show the superior performance of the metasurface, we compare it to a more conventional narrowband approach, where in the narrowband case, only single frequency feeding is considered. To demonstrate our design procedure, we fabricate the achromatic metasurface using PCB manufacturing, and we simulate them using CST Microwave Studio, where we obtain the suitable geometrical parameters. The measurement method here is based on 2D near-field scanner inside a parallel plate waveguide, as shown in this figure. And here is the scattered field measurement results, where both the achromatic design and the narrowband design are shown. 5 different frequencies are plotted, in which the achromatic metasurface has a clear focusing operation with minimal focal length variations from 8.5 to 9.5 GHz. In contrast, the narrowband design has a distorted focusing operation with strong focal length variation within the bandwidth. We see that the achromatic metasurface has a more constant and consistent spot size than the narrowband metasurface. In terms of efficiency, we also see that the achromatic metasurface reach 80% focusing efficiency, whereas the narrowband metasurface only achieves a maximum 50% efficiency within the considered bandwidth. So in summary, we show that the first order approximation method of surface impedance can be realized to obtain LC requirements for broadband copolarized metasurfaces. And we also show that the Huygens metasurface beyond conventional single frequency operation can be experimentally verified, where we also show that dispersion engineering is also possible. And we show that the principle is very general and could be applicable to other forms of Huygens meta-atoms. So for any questions, please send me an email. Here is my email address. And lastly, thank you very much for your attention.